When two waves move through the same space at the same time, they interfere with each other, and we've talked about this before, that interference can be constructive or destructive. I want to look at that again. And basically, we're revisiting this thing called superposition. The principle or law of superposition just says that we can combine the amplitudes of two waves algebraically, and we just add them straight up. So if I had a wave that looked like this at exactly the same time that another wave looked like this, the net result is a wave that looks like this. The amplitudes exactly cancel each other and I end up with no wave at all. Okay, that is not entirely clear. So let's take a look at just an example of a triangular shaped wave. Okay? So I have a triangular shaped wave that's moving this way. And on the same string or rope or whatever's carrying this, let's say I have another triangular shaped wave that is opposite of it and moving this way. What happens when these two waves combine? Well, I'm going to drag this wave over, okay, so we can see what it looks like, one wave on top of the other wave. At this instant, okay, we algebraically combine these two things. So since this one's displacing this far and the other one's displacing equally as far, that means right there at that instant these two waves actually have twice the amplitude. Whoops, the wavelength won't change though, so that was bad. So these waves have twice the amplitude, so the resulting wave looks like this with twice the height. And then if we continue this process through and we grab this wave again and we continue moving it over, okay, then at this instant it's going to look a little bit different. This peak is going to be made a little bit higher. This peak is going to be made, well, that's not really a peak, but it's got this displacement plus that displacement again. It's also going to be higher, and this is also going to be a little bit higher. And so we might end up with a wave that is fairly narrow, but more squarish, because these added up to about the same height each time. Okay, law of superposition. Which just says, hey, algebraically add those things up and we get something cool. Now, what's cool about this is if you have two waves of slightly different frequencies that are interfering with each other. And this is what you guys saw in lab. So I have this frequency wave, and then I'm going to have one that occurs a little bit more frequently. So I have this frequency wave. Okay. What's going to happen with this thing? Well, you can see, let me put in my rest line. Right here, these two things are going to add up and give me a bigger wave. Okay? And here, they add up and give me a kind of dead wave. And then here, it's still kind of dead. Here, it's getting kind of bigger again. And it's getting kind of bigger again. And now it's back to being dead, dead, and then it might get bigger again. So instead of having this oscillation, we end up with a wave that sort of looks like this kind of thing, okay? And I don't draw that very good, so I stole this picture from hyperphysics, okay? And so I have these two waves that have different frequencies that are interfering with each other. And what we get is we still have this inner frequency, but we also have this envelope wave. Okay. And this thing, because the amplitude is getting bigger and softer, bigger and smaller, bigger and smaller, bigger and smaller, and amplitude well, the square of amplitude is directly related to the energy the wave carries. We hear this, if it's a sound wave, as difference in loudness or volume of this wave. And so we hear this loud, soft, loud, soft, loud, soft, loud, soft. And the occurrence of that loud, soft is called a beat, and the beat frequency is equal to the difference in the frequency of these two waves. And actually, I guess I should say the absolute value of those two waves. So if wave 1 has frequency f1 and wave 2 has frequency f2, then the loud, soft frequency, or the beat frequency, is given by the difference between them.